Thank you for the introduction and the opportunity to share my work with you all today. So I'm going to present a pretty new experiment that we're doing in our lab at Swarthmore with the goal of using a photoelastic granular medium as a way to look at slow deformations that occur in granular systems. So the system of interest for this project is a pile of a dry granular medium that's at its angle of repose under gravity. This certainly seems like a pretty simple system to explore, but it's actually a really nice prototypical system for looking at a fundamental question for dense granular systems. And that is the transition from rigidity to a flowing state in granular media. That's what's shown in the image here, and it's also shown in a demonstration that I have that I spend way too much time staring at. So right now this is in a rigid, stable configuration, but when I apply forcing by tilting our granular system above a certain angle above its yield point, the system then starts to flow. It seems as though there's flow only at the surface layer of our granular pile, and the bulk seems to be having no movement. But actually, there's a slow deformation that's occurring because of granular forcing from the shear applied above. And we'd like to understand more about this slow deformation in granular systems. We call this creep behavior. Creep is actually something that is exhibited by all disordered systems. So the magic here is that we need disorder and an applied stress, and we can observe creep in disordered materials. The granular pile just serves as one example of a class of shear granular materials that exhibits a creep motion of that type. The picture here serves as an example, and I'll go through the other examples here of creep in different disordered systems. For the case of a shear granular material, the granular shear above promotes a slow flow of the particles that are below. And at longer observation times, we can observe this creeping motion, the velocity of which has an exponential decay with depth. Granular systems such as this also serve as a nice idealized model for geological flows so that we can make connections to things like hill slope creep, where there's a subial deformation of sediments like soil under gravity. And that's exhibited with pictures such as this one. So by using granular physics experiments like the one I'll describe, we can hopefully make connections to creep that occurs at geological timescales. There have been recent lab experiments that have shown creep in fluid-driven sediment transport. So I'm showing some results from a recent publication in which they use tracking of particle motion as a way of observing three different regimes of behavior: a dilute suspension, and then as you go deeper, a more bit-low flow that then causes creep deep in the granular bed. And more broadly, this is something that's observed in glassy systems. Glassy systems creep at low temperatures under relaxation due to stress. So by understanding more about creeping in something like a sand pile, we can make connections to relaxation in glassy systems. So hopefully this conveys how abundant the creeping kind of or slow deformation is in disordered materials. However, it's not appropriately captured in some well-established models that describe the onset of failure or yield in the disordered granular system. So that makes for a fruitful area for an experimentalist like me to help to test modifications to such models. Here I have a few examples of what I mean by these different models. For example, for Coulomb failure, the onset of motion is supposedly due to like a principal stress above which the material will yield. But that doesn't capture microfailures that can occur in the system leading up to that point. Then there's the jamming transition that describes an idealized kind of onset of rigidity in disordered systems. It can just capture rigidity in granular materials, foams, glasses with this jamming phase diagram. But it's hard to kind of capture heterogeneities in the material as it fails within the jamming framework. And then lastly, there's the mutes of our rheology, which describes how forces cause a deformation in some material. And it's described in terms of an effective friction, mu, and how it depends on the dimensionless shear rate, the inertial number, I. In order for immune survivability to capture the slow deformation motion of creep, we need to then include a non-local length scale to accommodate these kind of behavior. So hopefully with the experiments, we can then complement these types of modifications to models as a way of testing the effectiveness. That's what's motivated the work that I'll share with you all today. Our goal with the experiment is to learn a bit about the basic mechanisms behind creep, and then being able to ultimately test these in modifications to creep to flow models, such as the one that I've described. We have an experiment in which we can also look at how stress redistributes in deformations in granular systems, and then hopefully be able to link behavior at the particle and force scale, the micro scale, to explaining the global sort of bulk behavior and properties of a granular system that is under deformation. We're also motivated by previous experiments and simulations that show the creeping behavior using a really sensitive optical technique, and also show the role that disturbances play in creep, which we make use of in our experiments. So here are a couple of figures taken from these previous experiments in which they use an optical technique to shine a laser onto a granular system as it creeps. From the interference pattern of the scattered light upon the different granular piles, say a pile of sand, you can get a pattern, a speckle pattern on a detector. And then correlation of the speckle pattern for successive images gives you a link to deformations that occurred in the pile. This method has been really powerful because it can capture deformations at the scale of microns, and has been used to show particle rearrangements and micro failures in systems as a system is tilted at increasing angles up to its point of yield, its angle of repose, as well as being used for really long observation times in the geomech lab to show that creep can occur even in the absence of external disturbances. They found that disturbances only act to accelerate the role of creep in the granular system. And we make use of that in the experiments that we do with our photoelastic granular medium. We apply a disturbance to our photoelastic system, and the power of using this approach is that we can get positions and learn a bit about the way that the system is packed and learn grain rearrangements, as well as complementary forces. We can also describe the system from the scale of an individual grain to the mesoscale, the intermediate scale, up to the bulk behavior of our system by using the photoelastic imaging technique. So for the rest of the slides, I'll share with you all some details about the experiment and some of the first few kind of analysis approaches that we have done in order to capture some of this information. So our experiment makes use of photoelasticity, which has been used pretty extensively now to study the mechanics of granular systems. For such an experiment, you have grains that are typically made from a polyurethane, and this material has stress-induced birefringence. So when the material is placed between cross polarizers, as stress is applied to the material, it rotates the polarization of the transmitted light. So stress is shown by a bright pattern that appears on the material. So the video at the top here shows an example of such. I'm just holding a single grain in between my fingers, and as you squeeze it, you can see the bright pattern that occurs between the cross polarizers. When you have hundreds or thousands of these grains, you can see the really cool stress patterns that are then exhibited in granular systems. I have a demonstration of that as well. I'm thinking it's probably kind of hard to see, but hopefully this is an incentive for you all to talk to me during the break and play around with the demo a bit. So we use this approach to study creep in a granular pile made up of photoelastic grains. The actual experimental setup is kind of shown in the schematic here with a side view and a front view, where we have our granular packing that forms a kind of a heap shape, and it's placed between cross polarizers. It's filmed using 2 cameras, and then we align those images in post-processing. One camera has a second polarizer that acts as an analyzer to give us these images like so, where we can nicely see the force chain distribution. And the other acts as a camera that gives us like white light images that we can use for particle positions. The grains are 6 millimeters and 9 millimeters in diameter. So we have a biodispersed arrangement of about 1,500 grains. Here's a picture of the setup in the lab space. And we formed a pile using what's called a localized source procedure. So the grains are falling through a funnel that's attached to the top of our experimental chamber. And we allow the grains to fall from this kind of narrow channel and flow, forming successive avalanches as a pile forms at its angle of repose. It is expected from previous experiments that by forming a pile in this way, it leads to a specific stress profile, where there's a dip at the center of our pile based on the way the force chains kind of arrange as the pile forms. So we did a quick test to kind of see if our experimental setup follows that expectation by looking at the intensity of our force chains from a set of images to see that indeed we see kind of just on a rough scale for where we found our pressure from intensity of our images, that we do indeed see a dip in the stress profile at the center of our pile. And we expect that that probably has some influence, the way that the pile is formed will have influence on the creeping behavior that we'll then observe. We then disturb our pile after some time of preparing the pile. We then disturb the pile using single grain impacts. A single grain is dropped from a fixed height above our pile at set time increments to act as a way of disturbing the granular system. The expectation is that this will accelerate the rate of deformations within our system, but does not kind of fundamentally change the physics. So this is a way of kind of testing that. Then we get two sets of data like the one shown here. The top is from our camera of the white light images, and the bottom is from the image with the cross polarizers. So we can see positions of grains as well as forces. Right now I'm playing a video simultaneously of some motion in the granular system that leads up to an avalanche that occurs. And from these videos, we can see small grain rearrangements in the top profile as well as force chain changes in the bottom video. So for the next few slides, I'll talk a bit about the initial steps that we've taken to start analyzing the data from our experimental setup. To get data at the system scale, we use difference imaging from our photoelastic images. So this is a nice way of seeing kind of at a global scale, how is our system changing as it is creeping and approaching that point of the avalanche, like I showed in the kind of raw videos from our system. The countdown timer is the time to where an experiment ends, which is when the pile starts to avalanche. And we see that, sometime before the avalanche actually occurs, we start to see changes in our system in both the force chains and in some grain motion at the surface. If you see white streaks, that means that the force chain has become stronger in the process of the experiment, and black means that the force chain was weaker than our intensity measurements could catch. So by taking one image and subtracting it from successive images, this serves as a nice way of capturing patterns of failure in our system. Do you have a question now?
Yeah, quick question. What was the perturbation you used? Is there a perturbation you impose, or is this spontaneous?
There is a perturbation at the start of this video. There's a single grain that impacted the at the top of the pile, and then we record what happens afterwards. So then we just kind of watch the pile and wait for an avalanche to occur, and we call the end of the experimental run when the system starts to flow. It's officially transitioned. Thank you for the question. Yeah, so hopefully you all are able to see that from the point of disturbance to the actual avalanche, we're able to see a few precursors to avalanches in the system in terms of how the force chains evolve through the bottom of the pile, as well as some grain scale motion. Our second is particle scale level. So we can track the system down to the individual grain, and this serves as a really nice way of capturing individual grain rearrangements that lead up to a flow or transition in our system. An example is shown here with an animation where we are now coloring the location of our grains according to how much the grains move. The red grains are ones that move above a position threshold that we set in our experiments. At the start of the experiment, we see just kind of decorrelated areas where grains are moving. They're kind of caught in a cage with their surrounding neighbors and are able to move a bit. It's similar to these kind of hot spots that were found using the optical technique that I referred to earlier. And then kind of eventually there's a lag between the initial disturbance and then ultimately the avalanche that forms, where we see at the surface a significant number of grains that rearrange. We capture this in a plot just showing the number of rearranging particles as a function of time up to avalanche, time to failure in our system. And we see that it's just sporadic rearrangements that are occurring in our system until suddenly the system starts to fail and flow. And then lastly, we get information at the mesoscale. So we've seen already that granular systems exhibit these force networks called force chains, where forces are kind of dominantly propagating through a system. So I refer to that as kind of our intermediate scale in our system, the force chain scale. We can find force chains in our image by binarizing our image based on an intensity threshold and then locating connected components. So this is a way that we define force chain segments within our system. And then we look at those force chain segments for any interesting details that may arise leading up to a flow event. Our goal is to connect behavior at the intermediate scale with our force chain segments to creeping behavior in our system. So we've done some initial measurements with this, looking at the force chain geometry. Here I'm showing an example of the force chain angles, where I'm giving a distribution of our angles before and after an avalanche occurs. From our preliminary data, it seems that we get a wider distribution of force chain angles in the region in which our system will ultimately yield, and then our lower angle force chain angles after that event occurs. But we still need to kind of explore that a bit to see if there's really kind of an interesting story to tell. Our last approach is to quantify the force chain distributions using quantity that's called G squared. As a force is applied to a grain in our photoelastic response, we get a nice fringe pattern. An increasing force leads to an increasing fringe pattern, and that can be captured by the gradient of the intensity of our image. We calculate that square of the gradient of our intensity image, or image intensity, sorry, and we call that quantity G squared. So it's kind of a rough way of calculating any changes in the magnitude of our contact forces in a system. It works especially well for images like ours that are relatively low resolution. We have about 20 to like 30 pixels per particle. So this works out pretty well as a way of kind of quantifying changes where we can't see force fringe patterns in great detail. So we did an initial kind of measurement of that as well, with the goal of looking for any signatures in our G squared as our system is exhibiting creep or yield. We observe peaks where our granular system is disturbed, and we observe kind of dips in our G squared at points where our system is failing. So in conclusion, I've shown you kind of, I'm better with time than I thought. So in conclusion, I'll share with you all the kind of beginnings of a nice experiment that we have in which we're using photoelastic granular media as a way of studying deformations in granular systems. Our goal is to learn more about the kind of rigid to flow transition in granular systems, and we want to use this approach because it has the power of being able to give us information at all scales in our system, to take particle and force information and connect it to the bulk behavior. So we've been able to show that with some preliminary measurements at the grain scale, mesoscale, and the system scale. And I'll use my last few seconds to thank the people that actually did the work for this project. So I am the lead member of the SWOT Grains Lab at Swarthmore College, and we are an undergraduate-only institution. So undergraduates took the charge of building these really nice experiments and analyzing the data. This project started with Edna when she was a senior, and it's since been taken over by Elena, who is a senior at Swarthmore College, and happy to say applying to graduate schools now. And we work in collaboration with the PennSed Lab at University of Pennsylvania with Doug and Nicole, who's been working in great detail on the creep experiments. And thank you all for this opportunity.
Thank you for this great talk and beautiful experiment. So I'm sure we have many questions.
I have questions about this, well, this summary slide, my two questions. My first question was in the bottom left, obviously the outer edge is the angle of repose, but then you have a slip phase. Is that 60 degrees or what angle is that?
I'm sorry, the angle formed here or?
Yeah,
I guess
yeah, the slip phase, how do you call it, like the sliding, like between the dark blue and the light blue. That's...
Yeah, so it is a slightly steeper angle than the angle of repose. So
do you know what the angle is?
I don't know the exact value of the angle. I'll have to look at that. So, yeah, I have to look at that. I'm not sure about that.
Okay. My second question, if I may, yeah, very quickly.
Sure.
In the top right, I was very intrigued by your picture. I loved your talk, let's put it that way. The evolution of your force chains, how it, you know, some of them were getting stronger, some of them were getting weaker. Was that, did you track whether that's a linear process? Like, is it linearly increasing and linearly decreasing, or is there some kind of ramp up and runaway process?
You're right. So it is a kind of ramp up process, and they are correlated with one another. So we did do some initial kind of tests of this by looking at looking at like brighter pixels versus darker pixels in these images. And there is kind of a sudden transition that occurs. But I think we need to do it with a few more experiments to just kind of make sure there is actually a consistent trend there. Yeah, but I think you're onto something pretty good. So yeah, thank you for the suggestion.
So following up on my question, you said you perturb it by dropping one particle drop, right?
Yes, sir.
So, and which would decay after some time.
Right.
So it will come back to a stable equilibrium. Now, wouldn't it be nice if you had some kind of continuous perturbation and yet have creep so that you can get a steady state, and perhaps that might be relatable to, yeah, you know, avalanches and some geological phenomena.
Right. So by that, do you mean kind of continuously vibrating the system, or?
Right.
Yeah, we could certainly try that. I mean, probably there are a few people in this room can maybe speak a bit about that as well. But there have been some other experiments in which the system has been vibrated or heated, for example, as ways of providing a continual disturbance. And that's something that we want to try as well. We initially started this experiment with that idea in mind, but finding that we needed to kind of find a sweet spot where the disturbance isn't compacting the system, or, well, at some points it would compact the systems, at some points it would start to flow. So I think that is something we need to really explore more carefully. Thank you for the suggestion.
More questions?
Cacey, thanks for sharing these results. Is there anything qualitatively different that might happen in 3 dimensions compared to these 2-dimensional piles?
Oh, that's a great question. I'm not sure if I have the answer to that. I don't know, actually.
How about you? Oh.
Thank you for great talk. I just wondering, is there a velocity difference between the within the location, light blue regions. I just am wondering whether it's slided as a bunch of the things or slide from the top. Or,
Oh, that's a wonderful question. Yes. So your answer is the grains are actually moving at different velocities. So I kind of showed two versions of this data. One in which I used just a single color to say, are the grains moving or not? But actually the grains kind of at the surface move at a faster rate than those deeper in the pile. And previous kind of experiments and simulations have shown that there is an exponential decay in the mean velocity of that region with depth. Right.
Thank you very much.
Yeah. Thank you.
More question? Yeah.
It's a really interesting experiment. I'm just wondering, I like the idea actually just have one perturbation, because what I see from your video is that there's a time lag, like from the beginning of the perturbation, then you start to see the development of force chain eventually lead to the collapse.
Yeah.
I'm wondering, is there maybe there should be a scaling law to scale this to the real world, so it's almost like we have a predictor for landslide based on some measurement of force chain, right?
Right. Yeah, I think you make a great point that we should try just a single perturbation and then waiting for a longer time period to see what we observed then, because it was pretty kind of based on trying a few things out and experience there that we decided to do repeated perturbations at different kind of time increments, but we can certainly try just a single grain too and see. The expectation is that ultimately it will creep. We will see a flow. It's just a matter of the time scales that we need to wait in order to see that happening. I mean, I guess I have a bit of time, so I could set something up and just let it run and see how it goes.
Thank you, Cacey. It's really interesting and leads to lots of thoughts about things to do. So I wonder, regarding the perturbation, are you always doing this from a fixed distance, or do you consider weakening going closer and closer to the surface, or perhaps even using a considerably smaller particle as your perturbation?
Right. Okay. That's a great point as well. For what I've shown here, we released it from the same height, and it was a grain that was one of the smaller size grains here. And we had a chute. I think I forgot to say this. We had a kind of tiny chute at the top closing off the funnel, and that was how we released the grain at different increments. So we could definitely modify the setup to do what you're suggesting, releasing grains at different heights, and then releasing grains that would have a different energy that it imparts on the system seems like a natural thing to try as well. So I appreciate the suggestion.
Okay. Thank you very much.
Okay, thank you.